0 means 0, 1 means 0, 1, 1 means 0, 1. Similarly, 1 means 0, 1, and 0 means again 0. Okay. So again you have got a 0, 1, then you have got 0. Okay. So that means you are changing the waveform from here to this waveform. Okay. So this is the, and this waveform, that means that this waveform is orthogonal to this. Means S1T is orthogonal to S2T. That we see that we did it this as it is, we are just changing it on its binary waveform. So we just, instead of doing that proper orthogonality calculation and doing integration, we just say, oh, it is Zij in that way. That means the similarity bit agreement and minus bit disagreement by total number of bits between SIT and SJT, representing a digital form. So similarly, if I have some sort of a 2-bit data set, okay, so 2-bit data set 0, 0, I will say it is like that. I have the actually say 4-array coding. Okay, say I have the actual data is like this. So now I understand this is one symbol, this is another symbol, this is another symbol. So I have the pulses are also like this maybe. Okay. So in this one I generate like this. So in that case, what do we do? So it is, that means we generally say H2 equal to H1, 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 and it is H1 complement. This is H1 complement. If you take this one, each row will be orthogonal to others. Okay. So in this case, you will see that I have some sort of a, I will explain for, so that means for 0, 0, 0 means you have some pulse. For 0, 1, that means say this pulse, I have 0, 1, 0, 1. That means more number of pulses. For 1, 0, I have another type of thing. So that means for 0, 0, and I just do it like this for 0, 0. Okay. So I have to send 4 number of bits over here. So what I will do, I have some sort of a means this is a 0, 0, 0, 1, 1, 0, 1, 1. Now 0, 0 means I will now differently code it, and please note it that this it is this star, this duration, this that means it is the symbol duration. Please remember, this distance, this time is symbol duration, and this symbol is the code word duration. These each one is called code word. Okay, his duration is code word duration. Okay, code word duration is some sort of, and what is that code word duration? T equal to 8 into TC. Now TC is some sort of this, or rather sorry, 4 into TC. In the next step, now this one is TC, that is code word width or code bit duration. Okay. Now, please note for real-time communication, this 4 into TC, that is equal to, or rather, for here I am. So that means this is my TC. For 8-bit, H3 equal to H2, 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 H2 bar. Now H2 bar. Now this one is TC. Now this one is a some sort of a T, that means code word duration, T equal to 8 into TC. Now what is my sim here for real-time communication? This is my bit duration. For real-time communication, that means this is my one symbol. One symbol is, now for MRE coding, M equal to 2 to the power k. What is my T symbol? T symbol is K into TB. Okay, this is my TB, and this duration is symbol. For real-time communication, what you have to do, this K into TB, that means say here 3 into TB, 3 into TB is equal to this 8 into TC. Okay, so what is TC? TC is 3 by 8 into TB. Okay, so you understand that the whole 3-bit duration, the whole in this same duration you have to pack 8 different bits. Okay, 8 different bits means actually you are not 8 different, you are not packing 8 different bits. Rather, what you are doing for 000 was say some or other, if I just take it is some sort of 8 different pulses. Okay, so now in this case, in that same duration, you have to generate another set of pulses. Each of 8. You see, that this is for this one you have to generate this. Similarly, for this one you have to generate. But here you are sending 3 bits. But here you are sending 8 bit equivalent information. You are not sending bits. You are doing waveform coding. Please try to understand. Now here what you are doing, say in pulses 1 1 1 means you are, say you are doing some sort of you have say, or here. So it is some. This is your one say 4-array coding kind of thing. Okay. This is your 4-array coding, n equal to the power k. Okay. Now k. So this t symbol equal to 2 into tb. 2 into tb. That is equal to 4 into TC. So this is your TC individual one, because that this is that for real-time communication, this code word duration and the symbol duration they are same, because you are rather putting more information into your representation. Okay. So now in this case you see that what is my TC? TC equal to TB by 2. Now what I am doing in this 000, what I am basically doing in the same duration. Okay, in the same duration, what I will do, say this is your bit duration. Okay, now TC is half. Okay, so 000 means what I will do, say I may do something like this. I will transmit like this. Now next one, say for 01, say I may do like this 01 01. It is all zeros. Now what I am doing, 0 1 0 1. Okay, so 0 1 0 1. Then next one is some 0 0 1 1. The same, you see, the same duration. It is the symbol duration. Actually, this is your 0 0 symbol. This is your 0 1 symbol. Then it is 1 0 symbol. In that 1 0 symbol, what you are doing, you are just doing this. That means 1 0 is 0 0 1 1. 0 0 1 1. And the next one you are doing for 1 1 means 0 1 1 0. 0 1 1 1 0. Now this one maybe so you understand, that means I have put the pulses like this actually. Okay. So this is the way of representing it actually. So now you see, this is what you are doing here. This is your symbol duration TS. Here you are breaking it into 4 different time span. But here I am breaking it in the same thing. This is your TS, the same TS. Okay, TS is your 4 TC. I am just breaking it in a different way actually. Okay. So now, so that means this. Now you see that say 0 I have. So now in that one symbol was represented. You see, symbol waveform was for 0 0 you have represented like this. But the code word waveform that I am representing as if red one. Okay. Now you see for 0 1, what you have done? You have represented in between some one. But what I am representing, I am doing for red one, I am doing my code word representation is this, then this, then this, then this, something like this. Okay, so though your symbol duration is something, but my code word duration, code word waveform is something else. However, 1 0, it is 0 0 1 1. So my code word example is 0 0 1. Okay. Now for the next one is my actual symbol. If the symbol pulse is like this, but I have done it is 0 1 1 0 0 1 1 0. Okay. So you understand that means if I don't do the channel coding, so this is one way of waveform coding. Okay. If I employ channel coding, then these red things will come into picture. Otherwise, we will do this thing. Now, when you do this channel coding, you see that sometimes my waveforms, my original these data sets, I have represented. I have done the modulation in such a way that is pulse modulation. Maybe pulse modulation may not be orthogonal, but when I am doing this type of waveform coding, I can here also orthogonalize. Okay, that here yes, here that initially symbols are actually chosen in orthogonal fashion. On top of that, also I orthogonalize. But anyway, so even if these original symbols, pulse waveforms are not orthogonal, but here you can do the orthogonalization. Okay. So the basic, this Hadamard matrix for k-bit data set is basically hk minus 1, hk minus 1, and please remember that it is a k-bits grouped together cases. So that means you please try to understand that actually here you have 3 bits you are sending, but here you are sending 8 code words. Okay, so that means 3 into TB, that is equal to 8 into TC for real-time communication, because the total time you cannot change. That is equal to symbol time. Okay, so basically you are doing, so within that symbol you are just doing the juggler. Anyway. So now, so that's why as it is all binary kind of, that's why they have explained it in all 1-0 cases. Okay. Now biorthogonal code set, that means here, so that means I have, so for this is the case. Now let us do and that waveform coding. It has certain Biorthogonal performance, that it is some sort of a that probability of code word symbol is upper bounded by this type of Q functions. Okay, and they do certain calculations finally that beta also can be upper bounded by this type of functions actually. Now, what is the biorthogonal code? The biorthogonal code is, instead of Hadamard code, that is, it is hk minus 1 and hk minus 1 the complement. Now that means for a 3-bit data set, you see that means earlier for 3-bit data set, for 3-bit data, say iterative coding, I had to, what was the length of the code? Length of the code was, for 3-bit data set, my actual code word length was 8. But here what I am doing, here I have now for 3-bit data set, my code word length is, biorthogonal code word length is this. Okay, that is 4. So that means it is not that much. So that means if you change your, see in this case, you try to understand from 3-bit to you are changing 3-bit information to changing 8-bit of information, which demands more bandwidth. Why more bandwidth? You see that here you are basically you are doing more changes over here. So now in this case, so that means because in the same time you are sending 3 bits information, but here you are sending 8 bits of information. Okay, so in this case you are sending 2 bits of information, but now you are sending 4 bits of information. Okay, so now in this case we are rather balancing that actually. That means that V3 equal to this part is H2 and this part is H2 complement, and for biorthogonal set, actually if I calculate this Zij, that means the orthogonality measure kind of thing. That means if I equal to J, then it is one fine, but if I not equal to J and I minus J equal to M by 2, that means if I do now, what is the case? That means if it is similarity between this one and this one, that is anyway. But if you want to calculate the similarity between this one and this one, that is when I minus j mod I minus j equal to 4, that is m by 2, m equal to here 8, that I minus j equal to m by 2 means that difference mod of that one. Then it is minus 1. Then you see the number of agreements minus number of disagreements. Okay. Number of disagreements is 1, 1, 1, 1. 4 number of disagreements, no agreement, that is 0 minus 4 by 4, that is minus 1. So similarly, this one and this one, this is also Zij, Z, that 2 and Z6 is minus 1. So then that one is this minus 1. But when when I not equal to j, but I minus j not equal to m by 2, that means, say, if I take this one and this one, you see number of agreements 1, 2. Number of disagreements 1, 2. That is 2 minus 2, 0 divided by 4. That is 0. So this is basically combination of the orthogonal and antipodal signals actually. Please remember, though we are doing all in bit, but actually please remember this is also the data set. From the data set we have generated the waveform kind of thing for all 0, then 0, 1, 0, 1. So here you see what is your symbol duration? Symbol duration was 3 into T. Okay, each one is TB duration 3 into TB. Now that is equal to 4 into TC code word. Okay, so TC equal to 3 by 4 into T. Okay, so now in each 3 by 4 TB amount of time there is a change of information. Okay, so that means you see TB, sorry, this is 0.75 TB and this is TB. Okay, so that means this is 3 TB, 4 into 0.75, 3 TB. Now this one also, so that means this one you will do it in a blue one. Say you are 0, 0, you are representing by some pulses. Okay. 0, 0, 1 you are representing by another pulse. Say 0, 0, 1 you are representing by, say, sorry, no. So this one you are representing, this is symbol time. Now for this one 0, 0, 1, say you are representing by something, say some. Okay. Now for 0, 1, 0 you are representing, oh, sorry. For 0, 1, 0, you are representing by. For 0, 1, 1, you are representing by. Okay. Now here, this one you are representing, in the same time you are representing by 4 zeros. Then this one is 0, 1, 0, 1. Okay. So it is like that 0, then 1, then 0, then 1. Okay. So you see the bandwidth requirement here more frequently the change is there. Here the change was after TB, but here the change is after 0.75 TB. Okay, so that idea, right, that you are sending 3 bits of information, here you are sending 4 bits of information. So bandwidth requirement. And there is another one, Simplex code, that is just a simple thing, a code generated from orthogonal set by deleting the first digit of each code word. Is that transorthogonal or simplex code? Okay. So it is something like this. Okay. That means if I just drop, this is my orthogonal code. Now if I drop this first digit, see, I will generate the code from here. I will drop this. I will drop this one. Okay. Now, if I drop this one, what is about, say, Z12? Let me calculate that. The total number is M minus 1. Okay. M is 8 here. And what is the number of agreement and disagreement? This is 1 disagreement, 2 disagreement, 3 disagreement, 4 disagreement. Okay. Minus 4. Number of agreement 1, 2, 3. That means minus 1 by M minus 1. If whatever you do, it will be coming like this. Minus 1 by M minus 1. I am dropping this first column. So this is just a simplex code. And now please read this portion, that actually the simplex code for when the value of the large is M, this all three schemes, when M is large, then you will see that when M is large, what will happen? Do you think that when M is very big, that deleting the effect of only one column will that effect? No, it is not effect. So that orthogonal code set and this simplex code, this transorthogonal code, their the performance are same. Similarly for orthogonal, biorthogonal code also, because when M is very big, then M by 2 doesn't matter. That is for biorthogonal code, it is not like that. As a simplex and orthogonal, it is for a large value of M. Though regarding error performance, they are saying for all three schemes, but actually orthogonal and simplex. And this waveform coding means actually basically what they say, that means I have some MRE coding, I have M into 2 to the power A waveform. From there I am generating different these TCs. Each duration is TC, and I am generating the pulse, each rows, and depending by, so please try to understand these waveforms. They are all are the same way, and then they are generating so depending on the requirement, they are generating the rows. This generator means basically they are generating these particular rows or these particular rows. This is the generator, and finally they are doing some sort of a BPSK or something. So this is BPSK kind of phase modulation they are doing, or amplitude modulation. So this is the waveform, and similarly at the receiver, you are getting the receiver waveform. You have this each row information. You do the correlation. Finally, you take it is some sort of a correlation decision making. And the same thing, you see symbol time equal to k into TB equal to 2 to the power k into TC kind of thing for biorthogonal cases for coherent detection. Now, say rather I will talk about, so this the next is some sort of a types of error control. Okay. in that types of error control, there one thing is that we will do, sometimes we talk about error detection, and we will do the error detection and we will retransmit. Utilizes parity bits, I will come to it. Parity bits in some sort of a redundant bits that will add to the message data to detect an error that has been made. Now in this error control, there are three things, the requirement. So sometimes that you need only one simplex channel. Sometimes you need really a duplex channel. That means I will talk to it. That means there are three types of things. That means one is transmission in only one direction. Okay, this is some sort of a this connection. Often to their connectivity with their possible connections are in terms of simplex. Simplex, please remember, simplex means not that simplex code. Please remember, this simplex means not that I talked about this simplex code. It is, and simplex is some sort of a type of terminal connectivity. Simplex connectivity means the transmission is only in one direction. Now, there are two things. One is half-duplex and full-duplex. Half-duplex means transmission in both directions, but half-duplex means transmission in both directions, but not simultaneously. When you will transmit in this direction in one slot, then you cannot do transmit in the other direction. Or if you do this direction, then you cannot do the opposite. But when you will simultaneously do the transmission in both directions, then that is called a full-duplex kind of thing. So that they have explained, that half-duplex and full-duplex. So in this way, that means when we receive some data packet, and finally when we understand that there is some error, then what do we do actually? There are certain, this error control process is called some sort of a ARQ, or automatic repeat request. So this is some sort of automatic repeat request or automatic retransmission query. Means ARR or ARQ. Means both the terms are used. ARR or ARQ. AR or A. Now there are different methods. Now first procedure, that means this is called stop and wait ARQ. Stop and wait ARQ means that this is your transmitter, this is your channel, and this is your receiver. Okay. Now this is some sort of this packet, it is transmitting. So this amount is this is the time is moving towards right. This duration is called the transmission delay. Okay, so this packet has, and I am assuming that delay is uniform. Now this packet has been received. Now when the packet is received, there is some processing delay. After that, it is sending an acknowledgement. This acknowledgement is this is again the transmission delay for acknowledgement flag. So after receiving that one, that is processing delay. Then it is actually preparing the packet. This packet again it is sent, and okay. And please remember this transmission delay is same as this transmission delay. I am assuming that. Okay. And again you are doing the acknowledgement. Say suddenly here I have detected an error. So how will I detect the error? That I will come to it later. So say receiver has detected this packet is erroneous. So what we will say? You will say no acknowledgement. NAC kind of thing. It's a different symbol. It has received. Then what it will do after receiving that 3 not received, again he will do the repeat transmission. Then 3 is received, then this 3 has gone here, then it will send ACK, then again 4 is received, 4 acknowledgement has gone, then it will send 5, and then if there's a NAC, then he will do the repeat transmission of 5. That is basically he is doing, whenever I have no acknowledge, then no acknowledge also will get the signal. That means he will wait. Means he has find out no acknowledgement means please try to understand no acknowledgement. I have received the packet has some error. How the receiver will calculate the error, detect the error, that I will come later. So then he will do these things. Now, so the next is that you see that lot of time, you see that the problem is that lot of time is wasted. Lot of time wasted. Okay. So you are wasting time. This is not a very good scheme actually. Okay. The next is, that means it is, sorry. So now it requires a half-duplex connection, because you see why half-duplex connection? That why I need half-duplex connection? Because when I am doing the transmission at that time, during this time to this time. Okay. During this time I am transmitting from transmitter to receiver, but during this time I am not sending anything from receiver to transmitter. But again, when this time to this time I am sending from receiver to transmitter, but I am not sending anything on the opposite direction. So it is so that means rather I am sending in both direction but not simultaneously. That's why it requires a half duplex connection only. Okay, but the problem is that lot of time it's a empty time kind of. That what is the problem? Is that they have a third message stop, and the second ARQ is, but the problem is that it is a lot of free slots. I mean, you are wasting time. The next one is some sort of a ARQ with pullback. Now try to understand that pullback. What is the pullback? Pullback is, that means say you are transmitting, then first of all, that is without waiting for the acknowledgement, you are transmitting 2. Okay, right. Without waiting for this thing, you are transmitting for 2. Okay. Now, during this time, you are sending acknowledgement. But when the acknowledgement has received, already that up to 4, say 5 have also transmitted. So it's okay. So now, in this way, you are irrespective of, means without waiting for acknowledgement, you are sending the packets. Okay. Now see why the name pullback. Actually, that at the 4 says the receiver has detected that there is some error. So for what he has done, please try to understand this acknowledgement for packet 1. This is the acknowledgement for packet 2. This is for acknowledgement for packet 3. When he has received the acknowledgement for packet 3, already he has transmitted up to 7. He is transmitting the 7. Okay. Now, so that means so during say this time, say that means he is doing up some sort of a full duplex resources, and this is some sort of a NAC4. Okay. Now, when he has received NAC4, he has already transmitted 8. So what he will do, that means now at this point he has seen that 4 has not been received properly. So after 8, what he will do, he will again start from 4. Okay, that means the transmitter has moved back, pulled back. Transmitter is being pulled back from the current state 8 to current state, the previous state 4. and then again he is doing 4, 5, 6, 7, 8 because he knows that I have transmitted up to 8 and I am doing this. Okay. Now when he is transmitting 4 to 8, so what will happen? That means say 8 has been received, so that means NAC. This acknowledgement, this is NAC 4. Now this is your 5, 6, 7, 8. In this way acknowledgement is going on. But when again 7 is some sort of an error. Okay. So this is NAC 4, then 5, acknowledgement 6, acknowledgement 7, acknowledgement 8. Okay. Now this is acknowledgement 4. Okay, because after receiving the whole thing, then only they do the acknowledgement. Acknowledgement 5, acknowledgement 6, NAC 7. This 7 packet is erroneous. When he has received, but by the time he has received NAC 7, he has transmitted up to 11. So what will do? He will be pulled back to the state 7, and then he has seen, oh, 7 is not transmitted properly, and I have already transmitted 11. So he will use that from 7 to again he will start the transmission. So it is called some sort of this is the ARQ with pullback. ARQ continuous ARQ with pullback. The previous one was a normal stop and wait ARQ. Stop and wait ARQ, he will wait for acknowledgement and then he will transmit. Stop and wait. But previous one is back, then I will do the repeat transmission. Something like that. I will pull back and I will do the repeat transmission. So this is this one, and the next one is some sort of a continuous ARQ with selective repeat. You see, this is also continuous ARQ. That means I will not wait for the acknowledgement, but I will have a selective repeat. Selective repeat means what? See, I am doing this thing. Now, this is some sort of a NAC 4. The 4 has been received after that. But by that time, 8 is transmitted. So, what I will do earlier, what I have done, after 8, I will be pulled back to 4. Again, you will do 4, 5, 6, 7, 8, something. No, but now I will not do this. In this scheme, what I will do? Oh, 4 has not been received. I will send only 4. After 4, okay, I have previously transmitted 8, so then I will do again 9, 10, 11, 12, 13, 14. Now at 15, when it is 15, after 15, at this point I am saying, oh, 11 is NAC. Okay, then I will again transmit 11, and then I will again move to, okay, I have transmitted 15, I am doing 16, 17, 18. This scheme is some sort of the most efficient, actually. But please understand the coding point of view also, it is a bit difficult. So there are 3. This is some sort of a ARQ kind of thing. Automatic repeat means retransmission query kind of thing. Automatic retransmission query. The ARR is automatic repeat. Okay. And another thing is that another type of error control. This is a forward error control. This is here you see in this way. So here you need half-duplex connection because you need a both side link. But here you are not doing simultaneously. You need simultaneously. You are not transmitting simultaneously to the both direction. But in these two cases, you are basically doing that you are transmitting in a both directions simultaneously. So here you need some sort of a full duplex, but here you need half duplex. Now the next is some sort of a forward error correction. This is called the forward error correction. In the forward error correction thing is that you need only one way link. That means a simplex link. In this case, I will add a parity bit. Okay, this parity bit you have most probably you have studied already in your digital electronics class, and for the detection and sometimes the correction of the errors. Okay, and in the forward error correction is good. Why? Because I will save my bandwidth and I don't need the both directional network resources. Okay. Now in this that so now APC may be desirable in place of addition to error detection. It has some certain that reverse channel is not available with sometimes the reverse channel or the delay of the ARQ may be excessive. Now retransmission strategy may not be convenient implemented, or expected number of errors may be require the excessive retransmission. Okay, because when you do the say pullback, you are basically using a huge bandwidth. Okay, that you sometimes that if the channel is bad, that is you will find a very repeated retransmission, even with selective retransmission. Then also you are just capturing the bandwidth actually. Basically, you are not trying to correct, you are just repeating the packets actually. Okay, so and that next, so that means now we are talking about that structured sequence. Okay, the structured sequence means I will in the structured sequence I have some sort of a one is some one means in structured sequence one is some sort of a parity check codes, and the other codings are block convolutional and top code, convolutional code, and turbo code. So in this channel model at this point it is not required. From here we will move to this this parity check code. That means one is the parity check code, and is rather parity code or parity check code. Okay. Some sort of a parity check code, and then block convolutional and turbo. And in the meantime, please try to understand this convolutional and turbo. These two codes are used in standard communication protocol. Nowadays, what you do, normal 4G, 3G, all these communication protocol, either most of the time it is turbo is used. Please remember. So, and sometimes convolutional also used. Okay. But block code is simple. For simple communication, people use block coding kind of. Anyway, so we are not talking about these channel models, but if you want, you can read it. Okay. Now here there is term code rate. Say you have the source data. Okay, you have a source data, some sort of a 0, 0, 0, 1, 1, 0, 1, something like that. Now what you do, say this is your code block. This is your block of data. It is some sort of a k number of data. It's 2, 4, 5. Message. Now what you do, that means that the encoder, I have a channel encoder. Channel encoder will take each of kb data block. That is, this is one block. Then 2, 4, 5. This is another block. Now, each block, take each block. You will take each block. Add some n minus k number of bits. Return some bits n minus k number of bits, and make it. So that is k and n minus k. So that means output will be n bits block. So that means, say my encoder will take k bit, will give the output of n bit. Okay. Say that means it is taking 5 bit, giving 6 bit. Okay, that means adding 1 bit. Okay. So that means the code is some sort of a, we say that 6, 5 code. That is 5 is input, 6 is output. 6 is 5. The encoder took to 5 bits input block size and giving output 6 bits output block size. Okay. And what is my redundancy? Redundancy is that means that extra information, this n minus k number of bits it is generating based on the information from this one. Okay. So that means this is the extra redundant function. Here the bit streams are independent, but from here you are deriving. So that means you are doing something like that. I will do OR of XOR of all these blocks. This XOR means 0 0 XOR is how much? 0 0 XOR is 0. What is the XOR of 0 0 0? 0 0. A B bar plus A bar B. A B bar 0 plus A bar B, that is also 0. So that means 0 0 is 0, 0 0 is 0, 0 1 is 1, 1 1 0. So that means I will add, that means I will in this n means I will add 0 0 0 1 1 0. So that means this is my, so these bits and extra bits that it is dependent on this one. So that means this is some sort of a redundancy I am putting. Okay. So that redundancy, the ratio of redundant bits now to the data bits n minus k by k, and code rate is called k by n. That means that code rate is called 5 by 6 actually. That 5 by 6 is called the code rate. Okay, this is called code rate. Now when the code rate is half, that means your redundancy is, that means your code rate is half means, that means you are taking some sort of a 5 bits and generating 10 bits. What is your code rate? K by n, 5 by 10, that is half. That means 100% redundancy. That means for each 5 bit you are adding another 5 bits, 100% redundancy. Anyway, so now when you are adding number of bits, you understand that you are basically putting pressure on the bandwidth. Okay, so and there are so in many times we talk about code bit, channel bit, code symbol, channel symbol. Okay, so this is some sort of a same thing. Means we explain actually. So generally we talk about code bit and channel bit, code symbol, channel symbol. These are favored for MRE case actually. Okay, now and so next class we will talk about this parity bit or parity check of code. Okay, here there are two things. One is the even parity and another is the odd parity. Okay, and we will say Saturday tomorrow I cannot take class because I will be going to Calcutta. I will try to take class on Monday. Okay, so there we will start about this parity check codes actually. And what about the class test? When can we take this scheduled test? Sorry, not class test. When can we take the scheduled test? Maybe we will discuss it on Monday. Okay, thank you very much.